We're going to be looking at example 1D in your section 4.4 notes. So we'll start off again with the basic graph info. This function involves a square root. So we cannot take the square root of negative numbers. So one thing to note right away is the smallest square root that we can take here is -3. So our domain, we'll be drawing this from -3 on over to infinity. Next up, we can look at the x-intercepts. So for the x-intercepts, we would set our function equal to 0. Okay, when we do that, we're going to get two answers for 0, x equals 0 and -3. So those are going to be our two x-intercepts. For our y-intercept, we would plug in 0. So f of 0 will be 0. So we will get that as our y-intercept, which isn't a surprise because of our x-intercept. And that's really all we need as far as the basic graph info goes. So we will not be on the side of -3 when we draw. We'll start at -3 and move over. And we have an x-intercept here and then an x or y-intercept there at the origin, okay? All right, for first derivative, we are going to have to use the product rule. So I will leave the x alone, and then the product of that square root is 1 over 2 of that square root. Next, if I take the derivative of x, so that is 1. So I have 1 times this square root. All right, so we really need a common denominator at this point. So our common denominator is going to be the square root we have. So I need 2 with the square root of x plus 3. So that means we need a 2 on top, and then we're going to add another one of these, so we actually can just make that a square. All right, so right now we have our denominator is 2 with the square root of x plus 3. We have an x, and then we're going to add. Well, we're going to have 2 times this quantity. The square and the square root will cancel out. Okay, so we need to combine like terms up top there. We'll have a 2x plus 6 from this part. So when we combine that with the x, we'll have a 3x plus 6. Okay, all over 2 times the square root of x plus 3. Okay. So we get a critical point from looking at the top. So we can see that x equals -2 would be the answer there if we set that equal to 0 and solve. And then we can see from the denominator that x cannot be -3. So division by 0 is not allowed. So when we go to do our first derivative test, we're going to start at -3 anyway because of our domain. Okay, move on out. Okay. Probably the easiest side to test is this side. We can use a number like 0. So if we plug a number like 0 in, we'll get a positive number. Okay, the harder side to test is this one. You have to use a number like -2.5. When you plug that in the first derivative, you end up getting a negative number. Okay, so that tells us our function f is decreasing on the interval from -3 to -2. Our function is increasing on the other side of -2 on out to infinity. And then this also tells us if we're going down on one side and then up on the other side, that f has a local min at the value -2. And to find the y-coordinate, we go back to the original function, and we're going to get -2. And when we plug -2 in here, we'll get the square root of 1. So our answer ends up being -2 for the y value as well. Okay, so we might want to go ahead and take that into consideration. Okay, so -2 is our low spot, and we know we're decreasing on one side and we're increasing on the other. So kind of sprout that so I can keep in mind when I go to fill in after the second derivative info. All right, so the second derivative, this is going to be a little bit messy because this is our first derivative. So we need to use the quotient rule here. Okay, so we usually start off and we square the denominator. So if we square the 2, we'll get a 4. And if we square the square root, we'll just be left with the expression x plus 3. So the denominator is no problem. The numerator is where we get into some hang-ups. So we write the expression first from the denominator. Okay, and then the derivative of the numerator is 3. Okay, now we write the numerator expression, which is 3x plus 6. Okay, and we want to take the derivative of the denominator. So we have a 2 already, so we're going to be multiplying by that 2 that we have. And then this square root, right, when we take the derivative of the square root, it's 1 over 2 of that square root. Okay, so the good news is that the 2's are going to cancel. Okay, so we can get rid of that part. But we have that extra fraction bar upstairs that we're going to have to consider here. All right, so cleaning up a little bit so I can see what I have going on. I have 6 times the square root of x plus 3 right here. Okay, then I'm going to have minus. This I might as well put over my square root. So I have 3x plus 6 over the square root of x plus 3. Okay, and then my denominator, you can work that out or just leave that. It's actually probably easier to see the bad value if you leave it factored. Okay, all right, so working out this, I can definitely see that x can't be -3 again, just like the first derivative. So the numerator that I have, I want to set that equal to 0 and try to solve. So I'm going to do that off to the side here. So 6 times the square root of 3, or excuse me, the square root of x plus 3. If I set it equal to 0, I'm going to go ahead and move this to the other side. And so I can have positive 3x plus 6 all over x plus 3, right? Maybe a good thing to do at this stage is to cross multiply. It's a nice easy way to clean the fraction up. So I have 6 times, these are going to cancel each other, so it's 6 times the expression x plus 3 equal to 3x plus 6. Okay, not so bad from here. You get 6x plus 18 equal to 3x plus 6. 3x is equal to 12, and then x is equal to -4. Now that can't happen because we said from the beginning we're only drawing this function from -3 on over to infinity. Okay, so we won't need the value that the numerator gave us. All right. Okay, so as far as the second derivative test, all we know is we have a function that starts at -3 and goes on out to infinity. So the concavity has to be the same for the whole domain. So if we plug in a number like 0, okay, and go back here and test it, not so bad plugging in 0, even though this is a mess. The denominator is positive, so, and we plug in 0 here, we're going to end up getting a positive number. Okay, so that tells us that our function is concave up for the entire domain from -3 on out to infinity. Okay. And actually we can draw from there. So we knew that we were going to be dropping down to -2. Okay, so I can go ahead and connect that up. And then we knew we were going to be increasing because of the first derivative information from -2 on out. And we're just going to keep increasing and going up like that way. And we can definitely see that we have a concave up graph. And that completes this part.